Again, my name is Sonny Scroggin, and I have been involved in the Elixir community, I guess, for going on like 4.5 years now. It's flown by, it seems. And so I've been getting myself involved in a lot of little interesting things that I find interesting, at least. And so one of those things is writing more efficient programs in Erlang or Elixir within the Beam ecosystem. And so this talk is called Taking It to the Metal, and it is basically targeting folks who are interested in learning how to write native functions that are not going to crash the Beam or do lots of other terrible things that are possible. So with that, I would like to thank my company Bleacher Report for allowing me to be here today. And we are hiring for various positions, so if you're interested, please let me know. All right, so as Torben has his own the golden trinity of Erlang. This I call the holy trinity of Erlang, which is the concurrency, fault tolerance, and distribution. We all know this. This is why we use Erlang. But obviously, when we talk about native functions and things like that, there's always like a big giant warning and things like that. But one of the great things about the Erlang ecosystem and the Beam itself is that it's a fantastic orchestration platform. So there's all these different ways that you can use the Beam to interact with the outside world. And so we have ports, we have Erl interface, we have C nodes, or possibly even Rust nodes, for instance. We've got port drivers and native implemented functions. So there's all sorts of different ways that we can actually interact with other things outside of the Beam. And some integration examples of that. So Mix or Rebar uses Git, uses ports for external communication to go and fetch your dependencies and things like that. Erlang's inet driver is a port driver for networking. It's written in C, supports TCP, UDP, all that kind of stuff. And then another example is Jiffy, which is a well-known JSON encoder and decoder library. And that, of course, is implemented in C as a NIF. So why would you write a NIF? You might want to write a NIF if you need to, well, backing up, first off, NIFs are obviously native implemented functions. They're usually implemented in C or C++, for instance. And generally, it's like reserved for wizards, people who actually know how to slang C code without destroying the world. So why would you want to write a NIF? Erlang was really not designed for raw CPU throughput. Erlang's fast, generally, for most things, but sometimes you really need that raw native power. And so particularly, you might also need to deal directly with hardware, which you would need to be able to do that from some other language. Maybe you need to interact with a graphics library or of some kind. Or maybe the functionality that you need already exists in some other library that's already been written, and maybe it would be far too costly to re-implement everything in Erlang or Elixir. So the reasons why you would not want to write a NIF really come from the documentation. You have this giant warning that you read immediately. Obviously this functionality needs to be used with extreme care. You can do all sorts of terrible things, including crashing the Beam entirely, which really defeats the purpose of using Erlang in the first place. And so you have to keep these things in mind. So NIFs can be called just like any other Erlang or Elixir code. The NIF itself lives in a dynamically loaded library. So you can, when the Erlang or Elixir module is being loaded into the Beam, it is actually going to load the native code and replace the implementation with the normal Beam code and load the native function. So functionality itself, really NIFs are pretty simple in terms of what they can do. They can just read and write Erlang terms. You can deal with binaries. There's these things called resource objects that I'll kind of show you in a bit. But you can also do interesting things like threads and concurrency, which would be threads that are outside of the scheduler threads and such like that. Typically, if you're using Elixir, all the code examples for the Beam languages are here in Elixir. But we have this onload module attribute. You can specify the function that you want to call when it's loaded. And here we have an init. We're saying call the init function. Inside the init function, we will kind of find our dynamic library by using the privdir and pointing it towards the actual .so file if you're on a Unix system. If you're on Windows, it's probably a DLL or something like that. And then we'll tell Erlang, go ahead and load this NIF. So, and then we have our actual NIF functions, which these are going to be replaced when the Beam loads. The actual implementation here in the body of the function just is going to return an error if there was a problem loading the NIF in the first place. You could, however, instead of returning errors here, you could actually have some sort of Erlang or Elixir implementation of the function. So in the case that there was an error while loading the NIF, that it would fall back to a different implementation. So let's take a look at the structure of a NIF in C. This is kind of from the Erl NIF API. Provides us these various things here, so we can include the header file. All of the functions that you create for NIFs have the same exact structure. It takes an Erl inv type as the first argument. We have an integer containing the number of arguments that the NIF takes, and then we have basically a vector of NIF terms that you can use to read and write from. And then all NIFs return the same type, which is this Erl NIF term type. The Erl inv is pretty much just it's an opaque type. It basically is there to it's there for all of the terms to exist within, and they're kind of bound to each other, and they exist within the same lifetime. So it represents an environment that can host these Erlang terms. You can also access things like the calling PID of the NIF, and so you can kind of send messages back and forth to it as well. Erl NIF term is very similar. It's just an opaque type, but you can use the API provided to check which types the thing is, and you can do various things for encoding and decoding and all that stuff. So this thing down at the bottom is how you kind of export your NIF until how it loads and how the functions in your NIF actually go into the actual functions inside of your Beam code. And so you have this Erl NIF funcs, which is an array of structs, which each one just kind of maps the two together. And then you just export it finally here with Erl NIF init. You pass in the module name as the first argument. In this case, when you're using Elixir, all Elixir modules are prefixed with Elixir dot before the module name. Then you pass in your NIF funcs and then a bunch of other things that are not important at this moment. So I'm sure that there are plenty of you in here that are totally have written NIFs in C and you know what you're doing, but that is not me. I have never really learned how to write C, and I've heard too many horror stories to even want to attempt that, especially nowadays since we have other options. And so that brings me to the interesting bit of this talk, which is Rust. So Rust is a systems programming language. It's been developed around for about 4 years or so by Mozilla. And on their website, they say that Rust is a systems programming language that runs blazingly fast, prevents seg faults, and guarantees thread safety. So there's a lot of promises in that statement, and I think it's pretty interesting that they've actually been proven to show that it is, in fact, not just some marketing thing, but it's actually a real sort of awesome thing there. So, so Rust itself has all these excellent features. They've got things like zero-cost abstractions, threads without data races, and the last thing down here, if you can actually read that on the picture, is efficient C bindings. So a couple of years ago, I was really starting to try and get into Rust, and because I wanted to see if it was possible to actually write NIFs in Rust. And so I kind of had this idea, and I thought, surely if I myself am thinking about this problem, I'm sure someone else much smarter is already working on it as well. And so I kind of went out to find the way I could interface Elixir or Erlang with Rust. And so luckily enough, I came across this library called Erlang NIFs. And it's a crate, which is the kind of unit of, or like a package in the Rust ecosystem. And I found this library, and it's really nice. It just wraps the C API with Rust types, and has the ability for you to kind of use the Erlang NIF API, but with Rust. And so when you do use this, though, you'll find that it's quite low level. It's very much almost like using the actual C library. And so I thought, maybe we could like build an abstraction around this and wrap it so that it's much easier to use. You could potentially like protect people from doing stupid stuff at compile time. And sure enough, I was again lucky enough to not have to write this myself. Someone had already started a project called Rustler, and 2 years, I guess, year and a half. No, I guess it's been almost like a year and a half ago or so. I wanted to give this talk, and so in order to give this talk, I actually needed to actually kind of start writing some stuff, and so I was trying out Rustler, and at the time, it didn't compile on Mac OS. There was some changes that had been made, and there were problems with it. So I got involved, and I started submitting pull requests to fix things, fix the CI, and all that kind of stuff. And Hans, who's the creator of Rustler, was happy enough to make me a contributor, and so we've been kind of going back and forth and collaborating on a lot of different ideas about this thing. So Rustler itself, again, it's like a wrapper around the NIF API that allows you to write safe NIFs that will help you from shooting yourself in the foot and destroying your Erlang nodes. So provides different facilities for encoding and decoding Erlang types to Rust types and vice versa. And it catches any Rust panics before it unwinds back into C, which would then cause a panic in C and take down the VM. And so one of the goals of Rustler is that you should never be able to write a NIF that would crash the beam. And so far, I think that's pretty accurate. There are some edge cases that are still possible, unfortunately, but it's definitely rare. All right. So a quick getting started on this. We're going to go ahead and like kind of. Everyone builds their own JSON library, so I decided to do one too. And so you can start off with the mix tool, mix new JSON. You add your Rustler dependency, and if you want to use master, you can. You just use this cool little sparse option because Rustler is like the Elixir code base and the Rust code base are all in one repo, but it's in a different directory, so you can tell it there. Then we fetch the dependencies, and we have a little generator that allows you to generate some boilerplate for creating your NIF. A couple other things you have to do to get started. you set up the Rustler compiler. What this does is it actually calls out to the cargo toolchain, which is the Rust toolchain for building and all that kind of stuff, and it automates that so that when you run mix compile, it will compile your NIF and put it into the correct spot and also symlink it into the priv directory. You can also have some configuration here for your crates that are available. You can have multiple crates in a project. Oops. And so down here we have the Rustler crates. We just specify here's the path where the source code exists. We can specify the mode. So when you're in development, you probably want your NIF to compile in just as quickly as possible so that you're not sitting there for days whenever you make a change. So you can specify the mode based on the mix environment. So if you're in development or test, you could use the debug mode, or if you're released into production, you'd want to use the release mode. And that will take longer to compile, but it will make your NIF extremely fast, or as fast as possible. All right, so with Rustler, you also get a couple of conveniences here. We can go from this to this. It handles the init callbacks and all that kind of stuff for you. And so, yeah, we just specify use Rustler. We can specify how to get some other configuration. This is mostly just to infer the name of the library itself. All right, so here's our first bit of Rust code. We have a librs file. We have some macro, we are pulling in some extern crates. Those are the external library dependencies that we depend on. So we have Rustler and another thing called lazy static, which is for statically allowing us to create atoms that will always be around and never go away. So we are also pulling in an external crate called JSON, because why build your own JSON library when someone's already done it in Rust? And we have a couple of different modules here. We have one called decoder, and then we have one called atoms. And atoms just holds our atom table. And we have a macro here called Rustler export NIFs, and then we can specify. It's very similar to the Erlang Erl NIF init. It takes the module name and then an array, of the kind of like tuple structure that would be the mapping from the function name in the module to the actual pointer to the function in Rust. So, and this here is the arity, and that's the pointer to the function. All right, so this is like the simplest approach here, where we're going to use an existing Rust JSON parser that's already fast and efficient. We're going to decode a binary string into Rust types, and then convert those Rust types to Erlang terms. So this is the decoder .rs module and our decode function. And so here, all NIFs are very structured very similar to the Erlang NIF API. We have an environment as the first argument, and then we have, instead of the an argc like a count of the terms, we just have a slice of terms, which allows us to just simplify the API. And then the return type is not just a single thing, but we actually have what's called a result. And a result is like a monadic type that can be either something like OK or an error. So it's very similar to like OK and error tuples that we're very used to in Erlang, but there are like a lot of niceties in Rust that allow us to do things like this, where we can say, hey, let the data equal the args, whatever's in arg0 dot decode, and then we have a question mark operator on the end. And what that will do is, if it's able to unwrap the value and it's OK, then it will just return the actual wrapped value inside of that and give us that value directly. If it's an error, then it will basically do a short return and propagate the error up to the caller. So, and what happens here is that error is then turned into a very nice error message rather than just an explosion, right? So, all right. So then next we can do pattern matching, which is very nice. Not quite as nice as we have in Erlang, but Nice enough. So we match on this call to JSON parse, passing in our data. And if we get back, this is actually also, this JSON parse returns a result, which would be an OK and some value or an error. But in this case, we're going to actually match on it so we can actually make a nice error message if there is one. So if we get OK JSON, then we can call this function JSON to term, which will go ahead and turn all those Rust types into Erlang types. And then we can return an OK with basically a tuple. So we have, this is our OK, our atoms OK. So it's going to be an atom OK as in the tuple, and then the term itself. So it'll basically just be what we're used to. We'll receive back what we're used to in Erlang. And then in the case of an error, we'll do an error atom with the error itself, and all that's encoded. This is a recursive, this is the JSON to term recursive function here, and it just basically does what's on the label. All right, so let's time our NIF. So if we read in the file, some big JSON file, and we get the size here, it's about 8 megabytes. And if we use timer.tc and we pass in our module here, we can get the result back. And the time here, yay, 1.5 seconds. So about 8 megabytes of JSON takes about 1.5 seconds to decode there. So does anyone know the problem with that? Scheduler collapse? Yeah, it's definitely has to do with the scheduler, right? So part of that big warning that you get on the label when you open up the NIF API is in here. So a native function doing lengthy work before returning degrades the responsiveness of the VM and can cause miscellaneous strange behaviors. And the next bit sounds a lot like one of those drug commercials. Actually, we're in Europe, so you probably don't have those. But in America, we have like commercials on that repeat all the time about all these different drugs and side effects from those drugs, and it sounds a bit like that. So such strange behaviors include, but are not limited to, extreme memory usage and bad load balancing between schedulers. So yeah, so this is just a small portion of that error and that warning message. So there's a lot of things that can happen that can go wrong when you take too much time on the scheduler. So in fact, in the documentation and the warnings, really a NIF should take no longer than 1 millisecond. But I think that they should be even faster than that if they can be. So, all right. So let's take a look at some of the Erlang VM architecture and find out a little bit more about how this all kind of works and why this is a problem. So when you have a machine, the machine has a bunch of cores on it. And then, of course, we have the OS and the kernel threads. And when we spawn a VM process, we start up our application, we have an Erlang VM process, just one of them. And then inside that process the Erlang VM is going to spawn up 8 different threads in this case. So it's going to spawn up as many scheduler threads as you have cores. You can configure that to be less if you want, depending on your situation as well, but it can't be changed once it's been started. So there's also other threads as well for like I/O and things like that. But for this purpose here, this is a simplified version. So we have scheduler threads. Each one of those scheduler threads has a run queue. It actually has multiple run queues, but the main one here that we're going to think about is the run queue for all the processes. And so each run queue has a bunch of processes, and it's just like basically a stack here, and it pops off the next one, starts running the bytecode, and as it's running the bytecode, if it reaches something that calls out to something that's going to block, so for instance, if it says, hey, I need to read something from a file, or I need to read something off the network, or send something, then the VM, because it's running bytecode, can obviously preempt that process from doing any more work and taking more time on the scheduler, because it knows that it's going to end up waiting for the result to come back much later. And so the VM can automatically preempt that process. Now, if it's going to do something that's going to block indefinitely, or like if it's waiting for, if it goes into selective receive, for instance, like waiting for a message from another process, then it's going to do that as well. But if it's only doing CPU-bound work, then it can just keep going forever, right? Except for the fact that the Erlang VM has this thing called reductions. And so each process gets 2,000 reductions, which is not documented to be something very specific and concrete, but it's roughly equivalent to a function call. So it has about 2,000 function calls that it can do, and then it gets paused and put into the back of the queue. And so with that in mind, if you call native code, you no longer are running bytecode, and therefore the VM can't have that knowledge of what the process is currently doing. In fact, the code that's being run is being run in the thread itself, the scheduler thread, in that context. So it can no longer have control to preempt anything. All right, so there's also an interesting document in the Erlang OTP repo there. If you can make a note of the path on Erlang OTP repo. It's called thread progress. I still need to keep reading it many more times because it's pretty interesting and hairy. But essentially, thread progress is, in a nutshell, the schedulers share some data structures. And they protect them without locks or ref counts. So because that option wouldn't scale very well for the VM. And so instead, the schedulers essentially frequently report progress. And because of this progress, all the schedulers can kind of understand what data can be deallocated and what can't be. And so thread progress is really important, especially in the scheme of blocking schedulers. So when you block the schedulers, you end up preventing thread progress and making all the other schedulers wait. So, and a blocked scheduler can't be running processes, and so with that, obviously, a NIF should never take over the scheduler for too much time. Reduction counts also are not being taken into consideration when you're running a NIF in some cases. So you should also write NIFs that are well-behaved that also consume reductions. And so with that, we can kind of progress a little bit here and figure out how we can improve on this. So this is a little function that allows us to count reductions. The details are not all that important. We just ask the process, hey, what are your reduction counts before and then after running? And so if we look at this example again, after we run this, we get this little output here that we're inspecting. And so we can see that when we ran our NIF, we're only getting 10 reductions. So the thing took 1.5 seconds, and it only counted towards 10 reductions. So this is obviously not correct. So this should be much higher. So we can do better than this. So one option that we can do is chunking. Chunking is basically when you call a NIF that does a little bit of work, and then it returns back to you some stuff that you can use to call the NIF over and over and over again recursively. So we have to change a lot of things in order to do this, which really is a big bummer, because now that JSON crate that we were using, we have to throw that out the window, and we have to like write our own JSON parser in Rust. All right, so this is json.ex, our decode function here. We now have a decode init NIF and a decode iter. So the decode init is the function that we call first to like initialize the NIF, which then it will internally call decode iter and return to us some stuff here. So let's see, we call decode init. Then we call this decode result function, which is basically a recursive function that will recurse over itself based on what's returned. So in this case, if there's more work to do, we'll get back a more tuple with a resource and an accumulator, and then we just kind of like keep calling back recursively over ourselves. So this resource thing is pretty interesting. Resource objects are a safe way to represent a pointer to some data that lives inside the VM. If you try to inspect it inside of the Erlang side of things, it just looks like an empty binary, so it's opaque. You can't really do anything with it other than send it back into a NIF. Although you could, theoretically, you can actually share it with multiple processes and have kind of an interesting thing there where you can actually have multiple processes accessing the same memory within the VM. So that could be very interesting. Resource objects, again, they're not garbage collected until the last process, till no processes have reference to them any longer. So now our librs looks like this. We have changed a few things. We have now like a parser and a sync module. We have our two functions here for init and iter. And now we have this stuff here. So we have, at the end of our exports here, we're telling Rustler, hey, we want to do some initialization work when we're loading. So we have this load function where we are going to initialize a struct resource that's going to hold our resource here. And then decode init. We have a parser resource, which this is pretty interesting because because resources can be shared across other processes, we need to make sure that those two processes don't end up calling a NIF at the same time and trying to access this resource and causing mutability problems. So we have to wrap it in mutex to make sure that we get a lock on it. And so this one here, we now are decoding. We get our resource out of the environment here. We create an empty vector of terms, and then we call decode iter. So this is basically just like very quickly doing the setup to create the resource, and then calling the resource iter, which is the actual like re-entrant kind of NIF function. And so this decode iter function is very similar. It just gets all the stuff out that was passed to it, creates a sync stack that we can stick terms into, and then we call our parser, and our parser ends up essentially grabbing and trying to get a lock on that mutex, on that inner value. And if we can't get a lock on it, then we just throw a bad arg message. And then here we have this while not consume time slice. It just loops and loops and tries to parse more and more data. So this is actually going to be something where it parses for a certain time, and then as soon as while time slice returns, hey, you need to return now, then we quickly will return quickly return an OK value with the env and popping off from the sync. And let's see. Oh, I'm sorry. At the end here, we return atoms more with our args and our sync stack. So this is the way to return those values back into Erlang so that they can be chunked. All right. So our chunking result is quite a bit better now. We have 11,300 reductions. So this is much better. So now the NIF has only 2,000, or a process only has 2,000 reductions. So this was scheduled many times in the course of that 1.5 seconds. So it still takes a number of times to do it, but this time it's actually cooperating with the VM and making sure that it's well behaved. All right. So there's also other options for this as well, and one of them is rescheduling. The Erlang NIF API has enif schedule NIF, where rather than chunking on the Erlang code side of things, you can actually have the NIF itself internally chunk itself. Now, currently, Rustler does not provide an API for this, and the only reason why is because the NIF API has some some challenging rules that could make it possible to do bad things, and we can't really we don't have a current way to protect people from doing things incorrectly at compile time. So if we can come up with an idea around how to do that at compile time, then we'll add support for it. But for now, we're not going to support it. However, we have thought about making it an unsafe feature. So anything that's flagged as unsafe in Rust, it's like, hey, you know what you're doing, and you better do it right. Otherwise, you could do bad things. All right. So the other option is threaded NIFs. So the idea here is that a NIF will spawn a separate OS thread to do the work. And then once it's got the result, it'll send the result to the calling process. And so this changes up things just a little bit. We have decode threaded now, where we decode stuff. We spawn a thread, and we can now actually go back to using the JSON crate, because in this case, we're just doing the work in a separate thread, which is no longer going to block the scheduler. And we're returning immediately to the caller. So if the caller gets an OK atom in this case, and then it just waits in a receive block to wait for the result. So this is kind of the decode function in the Elixir side. So we call decode threaded, we get an OK value back, and then we wait in a receive block. And if we get OK result, then we're good. If we get an error, we pass the error, and then we can set a timeout if we want. After five seconds, we just return error timeout. All right, so another option is dirty NIFs. So now, since Erlang OTP 20, we have dirty NIFs on by default. It used to be an experimental feature, and now we have that is stable. And this allows you to call a NIF without worrying about blocking the normal schedulers. So now, when you start up the beam, you have your normal schedulers, but you also have the exact same number of dirty schedulers. And dirty schedulers allow you to say that I don't know if this NIF is going to run within a good amount of time, so I'm going to schedule it on a separate scheduler that's not going to affect the processes. And so this kind of allows us to do things that are potentially slower in VM terms and not affect anything in that manner. So you can do both dirty CPU and dirty IO, so depending on the type of operation you have there. So in Rustler, we have this scheduler flags here, which is dirty CPU and dirty IO. By default, it's just normal. So, with that, that is all I have. But I am really excited about this project because I think that writing NIFs has always been the scary subject for most Erlang people. And with Rust, it gives you this safety that you no longer have to worry about doing terrible things that could affect the performance or the stableness of the beam. And so this is really, really important. And I hope that this library can start to be used more, and also have more people, more smart people, actually contributing back to it and helping to make it better. Because I think that Rust has a lot of kind of guarantees that can help all of us to make better software and prevent terrible errors in the future. Thank you.